Hi, this is Dr. Goldstein, and today I'll be explaining related rates to you. So the idea behind related rates is that if two quantities are related, then their rates of change are related as well. So let's talk about what exactly we mean for two quantities to be related. This just means that there's an equation that contains the two quantities. So for example, I know that the area of a circle is related to its radius by the equation A equals pi r squared. So the area of a circle is a quantity and its radius is also a quantity, and they are related by this equation. Similarly, the circumference of a circle is given by 2 pi r, and so the circumference of a circle is also related to its radius. Now, we can combine these relationships if we want to relate other quantities. So for example, if we take c equals 2 pi r and we solve for r, then we know that r is c over 2 pi. And if we insert that into our area formula, we get the area is pi times c over 2 pi squared. And so if the area and the radius and the circumference are related, then area and circumference are related as well. Now, I can simplify this relation if I want to, if I need to do something with it, but the fact that there is an equation with the area and the circumference in them means that they are related. Now, let's talk about the other part of this idea. We need these two quantities to be related, and then if they are, we know that their rates of change are as well. And hopefully you remember that in calculus, the rate of change is precisely described by the derivative. So what we're saying is that if we have an equation between two quantities, then we also have an equation between their derivatives. So there is also an equation between derivatives. And the point of a related rates problem when you're given one is to determine what the quantities are, so what are the quantities, how are they related, and then how can I use information that's given in the problem in order to find some other piece of information. So what you usually have to do with related rates problems is to determine an unknown derivative based on some given information. So let's see an example of this in action. So let's suppose that the sides of a cube are expanding at a rate of 2 inches per minute. We want to know how fast the volume of the cube is changing at the moment that the cube has side lengths of 8 inches. So I've tried to draw a suggestive picture of a cube that is growing. So we know that this cube is expanding, and we are given that the sides of the cube are expanding at a rate of 2 inches per minute. And the problem asks us to relate that to how fast the volume is changing. So if we were to go through this problem and identify our quantities, we have the sides of this cube, which, because it's a cube, I can pick one variable for the length, width, and height, and I can call that S for side. And I also have the volume of this cube. So I'll call that V. Now, we know our quantities. We know that we have sides and volume. If you don't know it already, pause the video and think for a minute, how are volume and side related to each other? This is usually the hardest part of these problems, so take a moment, think about it for yourself until you get it. Okay, hopefully you paused the video and you thought about that. So the volume of a cube is length times width times height, and so in this case, those are all S, and so volume is S cubed. So this is our equation. This is our relation between the quantities V for volume and S for side length. Okay, so what the problem is telling us is to find how fast the volume changes. So we're asked to find how fast the volume is changing. So because volume is changing, we know that it is a function of time. This cube is getting bigger over time. So we note that V is implicitly, it's implied in the problem, V is implicitly a function, V of t, it's a function of time. And similarly, we're told that the sides of the cube are expanding, they're getting bigger, so also S is a function, S of t, of time. And so when we're talking about how fast the volume is changing, we're asking about the derivative of V, and specifically we're asking for the derivative of V with respect to time. So this problem is asking us to find dV dt, i.e. how much volume changes over time. Now we are also given some quantities. We are given that the sides of the cube are expanding at a rate of 2 inches per minute, right there. And so we are given that ds dt is equal to 2 inches per minute. So that part of the problem tells us that our quantities are measured in inches and time is being measured in minutes. Now there's one more part of this problem that we're given. We need to know how fast the volume of the cube is changing at the moment that the cube has side length of 8 inches. So we're asked to find dV dt given ds dt when S is equal to 8. And it's very, very important to note now that S is not always equal to 8. The length of S changes. The length of S is not constant. But we're asked to find the volume at this particular time when the side length is 8 inches. So we have a relation between the quantities, and we can take that to relate their derivatives by taking the derivative. So when I take the derivative of both sides, I am taking the derivative with respect to t, and I get dV dt is equal to 3s squared. And now remember that s is not just a variable, it's a function of time. So I have to use the chain rule is the same as implicit differentiation. I have to use the chain rule when I take derivatives, and I get that dV dt, the change of volume, is related to the change of the side length, ds dt, by multiplying that side length by 3s squared. That's what that equation is telling me. So now we're pretty much done with the hard parts of this problem. We know what we want to find. We want to find dV dt. We're given ds dt. We're given that we want dV dt when s is 8. So we're given ds dt, and we know what quantity we want to use for s. All we have to do is plug in. So now we plug in. And we have that dV dt is 3 times 8 squared times 2, which comes out to 384. Now it's worth noting that this is the rate at which the volume is changing, and so it has units, cubic inches per minute, because our time was measured in minutes and our quantities were measured in inches. So that is the end of this problem. The hard parts of these problems are figuring out your relationship and then correctly identifying what you're asked to find and the given quantities. Now, one notational detail that I want to emphasize. We are using Leibniz notation for these problems. And you'll notice that we had this equation v equals s cubed, and without any context, this equation is somewhat ambiguous because we don't know that v and s are functions of time. We could say, oh, v is a function of x. V is a function of side length. And in that respect, we could calculate the derivative of v, and that would just be 3s squared. So this is viewing the volume v as a function of side length s. And we could do this, and we would use the notation dv ds. The way that you would say this is the change in volume with respect to side length. But in the problem we just did, we were treating v as a function of time, and we were also treating s as a function of time. So we found dv dt, which was 3s squared ds dt. So this was viewing v and s as functions of time, meaning changing over time. And the way that we would say this quantity is that it's the change in volume with respect to time. And this rate of change here, so here when I take the derivative implicitly, where both of these are functions of time, I get two rates of change. And this one is the change in side length with respect to time. So again, related rates, we tend to use Leibniz notation because we want to be very specific about which derivatives we're taking, because we have quantities that we relate that are changing over time. We find that relationship, we take the derivative to relate these changes, and then we plug in our given information to find different information.